All right. So what's the explanation then for this anomaly? The way you explain this is by saying, well, since intensity doesn't depend, the kinetic energy of the electrons don't depend on intensity, then Einstein said, let's imagine light as a stream of photons instead, so that each photon carries an energy equal to h nu. Okay? Then you say, for a given piece of metal, there's going to be a minimum energy that you need that a photon must carry in order for it to dislodge an electron. In other words, if you have an electron on the surface of your metal, a photon, okay, interacts with one electron, okay, and if that photon's energy is higher than what's needed to eject the electron, so there's a minimum energy that a photon must have to eject an electron from the piece of metal. So if that is higher, if h nu is higher than h nu naught, okay, h nu naught we said, remember we said it's the work function. If it's higher than the energy needed to knock out one electron from the surface, then you can get the electron to come off. If h nu is less than h nu naught, it's less than the work function, then it's not going to come off. It's like saying, if I were to toss a bullet at the wall, okay, I won't be able to give that bullet enough kinetic energy to knock off a piece from the wall, right? That would be what you would call a low energy photon. Okay, that would be the analogy. But if I fire that bullet from a gun, I can knock off a piece of the wall with that bullet. That would be a high energy photon. So in other words, Einstein was saying that it must be this high frequency radiation must consist of photons that are very energetic. And that's what we said before when we talked about it. So we're now looking at it in hindsight. But that's how the idea of frequency being related to photon energy came about. It's to explain the photoelectric effect. It's in fact for this work that Einstein got his Nobel Prize, for his work on the photoelectric effect, not for relativity. Okay? So there's a minimum energy needed to dislodge an electron from the surface. If the energy of the photon is less than phi, it's less than the work function, your photon cannot dislodge an electron. If it's higher than phi, it's more energetic than the photoelectron. It will dislodge the electron. So what's the difference between h nu and phi? Photon energy minus the energy needed to remove the electron, the remainder becomes kinetic energy of the photoelectron. So let's say this thing has 5 electron volts, okay? Think of the work function as the bail to get the electron out of jail. Okay, so let's say your work function is 3 electron volts. Well, a photon comes along, hey, I've got 5 electron volts. Here, take the 3 so I can get you out of jail. And so the electron leaves. How much energy does the electron have after that? 2 electron volts will be the kinetic energy of the electron. So think of the work function as the cost of the ticket out of jail. If you imagine the piece of metal as the jail for the electron. Okay? And so the photon must provide at least that much energy, and whatever extra energy the photon has becomes kinetic energy of the electron. Okay? And higher intensity simply means that you have more photons. Okay, and so you get more electrons ejected, but a higher intensity will not give you more energetic electrons. So the energy of the electron depends only on the frequency, okay, which dictates what what tells you what the energy of the photon is. Okay, so intensity is related to energy in the sense that if you have something that's more intense, you simply have more photons. It's the frequency that determines the energy of each photon. Okay, so you might say that a million ping pong balls might have the same energy as one bullet. Okay, but this million ping pong balls you aim at the wall are not gonna get anything to come off the wall, but that one bullet can knock off a piece of the wall. So it's all concentrated in that one little particle, the energy. All right.